Hi guys, welcome to PreCalc day 4 on the matrices unit. We're going to do another day of Gauss-Jordan. We're only going to do one big example. I got another one that you can practice with if you want, but then I got a couple special cases. The idea of the infinite solutions where it's like the paddle wheel, and the no solutions which are like parallel planes or triangular or something like that. But let's practice this idea of Gauss-Jordan elimination to get a reduced row echelon form matrix, so then we can solve for x, y, and z. And again, process is everything. All right, let's create our 3x4 augmented. 2, 1, 1, 2, 1, 1, negative 1, negative 6, negative 1, negative 2, 2, and 10. And just to remind us, we want the main diagonal 1s. We want the bottom left and the upper right corner zeros, and whatever those three numbers in the last column are the x, y, and z values. And we have an order. We sort of like to go first, second, third, fourth, but it's not written in stone. Depending on the system, as you get better at it, you may jump around and see something that goes out of order, but it works better. So the first thing, I want a 1 where the 2 is. Yes, we could subtract 2 row 1s, or row 1 minus 2 row 2s. Yes, we could add row 1 plus 2 row 3s. But isn't the easiest way, guys, to just switch 2 rows? Let's put our row 2 there, our row 1 there. We did a switch. And again, you have to show the steps, how you turned red into black. Oh, he just switched. I got it. All right, now we want a 0 where the 2 is and a 0 where the negative 1 is. In other words, column 1, we want to be 1, 0, 0. So I'm going to do both in the same iteration. I'm going to take row 1. We're going to leave it alone for now because it's in row echelon. But again, we want it in reduced row. Row 2 minus 2 row 1s. 2 minus 2 is 0. 1 minus 2 is negative 1. 1 plus 2 is 3. 2 plus 12 is 14. Row 3 plus row 1. Stop and pause if you want to see if you agree with me or not. Do whatever you need to do on this video. 1 plus negative 1 is 0. Negative 2 plus 1 is negative 1. 2 minus 1 is 1. 10 minus 6 is 4. All right, we got our first column, the 1, 0, 0. I want a I want a 1 in row 2, column 2, where the negative 1 is. Easiest way I know is just to negate row 2. 1, 1, negative 1, negative 6. Negative row 2. 0, 1, negative 3, negative 14. 0, negative 1, 1, 4. We're getting closer. I want a 0 in row 3, column 2. Now, I could use either row 1 to get rid of it, or I could use row 2 to get rid of it. Which one are we going to use? And the answer is row 2. Because the 1 in here would mess up that 0. And we don't want that to happen. So we're going to 0, 1, negative 3, negative 14. We're going to take row 3, and we're going to add to it row 2. 0 plus 0 is 0. Zeros keep numbers. 1s get rid of numbers. 1 minus 1 is 0. Negative 3 plus 1 is negative 2. Negative 14 plus 4 is negative 10. Once I have the 2 zeros, that's when I multiply. So I'm going to go back to matrix black. My 4th iteration, 1, 2, 5th iteration. I'm going to leave row 1 for now. I'm going to leave row 2 for now. And I'm going to multiply row 3 by negative a half. 0 times anything is 0. Negative 2 divided by negative 2 is 1. Negative 10 divided by negative 2 is positive 5. I know what z is. Again, Mr. Ward, can we stop at REF? Well, if the directions say you can, then yes. If the directions say use Gauss-Jordan, then you can't. So we got 3 more numbers to get rid of. Blue iteration number 5. 1, 1, negative 1, negative 6. I'm never touching row 3. Tells me z equals 5. And what am I doing to row 2? I'm going to use row 3 to get rid of the negative 3. Row 2 plus 3 row 3's. 0 plus 0 is 0. 1 plus 0 is 1. Negative 3 plus 3 is 0. Negative 14 plus 15 is 1. I know that z is 5. I know that y is 1. 2 more iterations, and I'll get it into reduced, and I'll know what x is. I'm never touching row 2 or row 3 again. Row 1 plus row 3. 1 plus 0 is 1. 1 plus 0 is 1. Negative 1 plus 1 is 0. Negative 6 plus 5 is negative 1. And our last iteration, row 1 minus row 2. 1 minus 0 is 1. 1 minus 1 is 0. 0 minus 0 is 0. Negative 1 minus 1 is negative 2. 0, 1, 0, 1. 0, 0, 1, 5. There's my solution. X, Y, Z. Ordered triple. Negative 2, 1, 5. Again, the only ordered triple that would work into all 3 original equations. Go ahead and check it if you want to. I'll check it into 1. 2x plus y plus z equals 2. 2 times negative 2 plus 1 plus 5. Does that equal 2? Negative 4 plus 1 plus 5. 6 minus 4 is 2. It checks. And it's also the intersection of the 3 planes in space. All right, so that's a good one. I got another one here for you. You can practice this one in a little bit if you want to. I'll give you the answer in a second, but I want to move back to this. How does it show up to be a no solution? How does it show up to be an infinite solution? Well, here's what's going to happen. In your original matrix, you don't know by looking at it that it's a special case. But in your processes, you end up with this line right here. And what does that say if we put the variables back in? No x's, no y's, no z's equal 5. Can that happen? It can't. That is what happens when you get no solutions. And then just as important and requiring a little more work is what happens when you get this. Everything drops out, you guessed it, infinite solutions. But you actually have 2 more tasks. 1, you have to find a rule, how all 3 relate. But what that means is it's infinite solutions doesn't mean every ordered triple will work. It just means there's a lot of them and they follow a pattern. And then the second thing you must do is give 1 or an ordered triple. 1 specific set of numbers that follow that rule. How do I do that? Here's how. If I put the variables back in to that top equation, it says 4x plus 8y plus 10z equals 16. The second one, 2y plus z equals 4. What I'm going to do is solve everything in terms of y. You could do x, y, or z. I'm going to choose y, and I'll show you why right now. Take this equation 2 and get z alone. Negative 2y plus 4. Pretty darn easy. So right now, what do I know? I know that y, the middle term of the ordered triple, can be anything I want it to be. Whatever that is, z has to be negative 2 times that number plus 4. So now I want to get x in terms of y as well. and here's how we're going to do it. First equation, 4x plus 8y plus 10. I'm going to replace the z with what it equals. Negative 2y plus 4 equals 16. What do I have? I have just x's and y's. I'm going to solve for x in terms of y. 4x plus 8y minus 20y plus 40 equals 16. Combine the y's. 4x minus 12y. Move the constant over. 16 minus 40 is negative 24. Solve this for x. I'm going to divide through by 4. X minus 3y equals negative 6. So what does x equal? 3y minus 6. So now I can go back up here. I solve for all three variables in terms of 1. Whatever y is, the x has to be 3 times that minus 6. The z has to be negative 2 times that plus 4. I'm going to pick one ordered triple. For y, I'm going to pick 1. Nice and easy. Pardon me. 1 times negative 2 is negative 2 plus 4. Z must be 2. 1 times 3 is 3 minus 6. X must be negative 3. So that is a specific ordered triple. What I could do, I could plug that ordered triple back into this equation. 4x plus 8y plus 10z equals 16. 4x plus 8y plus 10z equals 16. 4 times negative 3 plus 8 times 1 plus 10 times 2 equals 16. Negative 12 plus 8 plus 20. 28 minus 12, it checks. So again, special cases, if you get a contradiction, all zeros but a number, no solutions, you're done. If you get a whole row of zeros, it tells you infinite solutions. You have to find the rule in terms of one variable and then give one specific ordered triple. What I also could have done down here, instead of that, I could have put a 0 in for y. That would have made, you tell me, x be 4, or pardon me, z be 4, and x be negative 6. And again, that would have worked. All right, that's the special case ones. One last one you might want to practice to yourself, with yourself, and why don't you, on your own, see if you can come up with, again, the process Gauss, Jordan, elimination, to get it into reduced row echelon form, to solve that ordered triple, and what I get is the triple 1, 2, 3. All right, guys, great work for today, day 4. We got some more matrices stuff coming up, day 5. A little shift, maybe a little bit more straightforward. Love this process, though. It's great mental gymnastics. Get you thinking, process related. Have a great day.